Hello students, welcome back. Let us resume our discussion in section 3. Previously, we went through example 3.4a. Let P be an odd prime and prove that -1 is a quadratic residue if and only if P is an odd prime of 4k plus 1 type. We went through that, I believe. You can rewrite this x squared plus 1 is congruent to 0 into x squared is congruent to -1, so that we get -1 is quadratic residue. Okay, we went through that. So this is a characterization of 4k plus 1 type odd prime. And let's use this to prove there are infinitely many primes of the form 4k plus 1. So P is a prime number, is coming from the set of all primes, but it's in 4k plus 1 type. And there are infinitely many of those. First, let's suppose there are finite many, P1, P2, P3 of the Pn, and then we're going to define this form, the product of all plus 1, but unlike the previous example that I showed you in the previous video, that there are infinitely many primes, a review of what we did in lesson 4, we took squared. And then we put 2 here, an obvious attempt to get 4k plus 1 form. Alright, now please observe that this, oh, sorry about that, I changed character and then I missed this. This capital Q is odd. This is an even number, 2 times something, so it's an even number, and plus 1, so that's odd. So it's divisible by an odd prime. Every integer greater than 1 has prime factorization, so it's divisible by a prime, and all primes that divide Q must be an odd prime. So on an odd prime, P divides Q, so we get Q is congruent to 0 mod P. Consequently, this 2, P1, P2 of the Pn squared is -1. So what do we get? Oh, -1 is a quadratic residue. Remember this? -1 is a quadratic residue. That means this prime P is a 4k plus 1 type odd prime by what we did in part A. Do you see this? I'm highlighting this right now. And we suppose that there are finitely many of those types and the P1 through Pn. So this odd prime P should be one of those PIs. So one of those PIs. So P is one of those PI. So what do we get? This capital Q is congruent to 0 mod Pi. And then look at this part. That's 0 because we multiply this Pi. So 0 plus 1, therefore Q is congruent to 1 mod P. Hey, which is right. 0 mod P, because it's divisible by 0, or 1 mod P. You see, this is 0 plus 1, so 1 mod P, or as you said previously, 0 mod P, which is right. They cannot be right both. They cannot be right at the same time, so there's contradiction. P divides Q and P does not divide Q at the same time. It can't be right. So there goes the contradiction. This contradiction, of course, came from the assumption that there are finitely many of them, P1 through Pn. And then for initial step, product of them all plus something, yes, we are using pretty much the same technique. The same technique we use to prove that Euclid's theorem, that there are infinite many primes to begin with. And we use this one too. It wasn't easy, but it was a beautiful result. by the way, we already proved that there are infinite many primes of the form 4k plus 3. Remember that in lesson 4? Let's review that. We already did it, so if you feel comfortable, you can skip, but I have a feeling you must have forgot it by this time. So let's go ahead and do that. So, just like the previous problem, P belongs to this double struct P, set of all prime numbers, and that it must be of this form, 4k plus 3 form. And that set is an infinite set. There are infinite many primes of the form 4k plus 3. Again, suppose that there are finite many of them, P1, P2, P3 up to Pn, and then we're going to define, similarly, product of them all, and plus 3 this time. An obvious attempt to get 4k plus 3 expression. Alright? Alright. Then, Q is not divisible by any primes of the form 4k plus 3 because that's 0 mod any pi and then plus 3. Oops. Okay. Alright. So it's not divisible by any pi. But then again, it's not divisible by any prime of the form 4k plus 1 either. Because if you take the prime factorization of Q, all the primes should be of 4k plus 1 form because it's not divisible by any of the primes of 4k plus 3 form. You see, we listed them all and multiplied, and then not divisible by any of those. So all prime factors of capital Q must be of 4k plus 1 type. But then again, if you multiply them all, and then you take modulo 4, why 4 is coming clear, 4k1 that's congruent to 0, 4k2 that's congruent to 0, all 4k's are all congruent to 0 modulo 4, so we get congruent to 1 mod 4. But then again, if you go back to this, it's 3 mod 4. 4 times an integer plus 3. So 3 mod 4. Ooh, which is right? 1 mod 4 or 3 mod 4? It can't be both right simultaneously. So the conclusion, the prime factorization should be of the form 4k plus 1. That's gotta be wrong. And certainly Q is not divisible by 2. I mean, the only prime left. So no prime divides Q. Not 4k plus 3 form, not 4k plus 1 form, and the final prime, 2. So there goes a contradiction. Every integer greater than 1 is divisible by any prime, divisible by some prime, and have a prime factorization, but this Q does not. So that completes all those proofs. Then what do you have? We went through 4k plus 1 prime, and the condition for that. -1 is a quadratic residue there, and use that to prove there are infinite many primes of the form 4k plus 1. And then we already did in lesson 4, but there are infinite many primes of the form 4k plus 3. And can we consider other kind of primes such as, 8k plus 1, 8k plus 3, things like those? And can you classify all those? Do you see any gaps there? All kind of problems will open up from there. Many of those problems are still an open problem. I mean, still open problems in plural. Okay, that completes both examples. Do we have enough time for one more? The sum of all Legendre symbol. Okay, alright, that's not too bad. Sum of all Legendre symbol for all A going from 1 to p minus 1 should add up to 0. Why? We have equal number of quadratic residues and non-residues, right? So equal number of positive ones and negative ones, they're going to add up and cancel all of them off. And if you define 0 of p as 0, then you can say 0 to p minus 1 add up to 0 as well. But some people do include 0. Most people don't. Our textbook author does not. So the proof is, well, pretty simple. Equally many quadratic residues and non-residues, and then 0. So p minus 1 over 2, that many plus 1s, and p minus 1 over 2, that many negative 1s, add up, you're going to get 0. And if you include 0, we get the next expression. If you include 0 into the mix, you can do that if you want to. Some people do, but most people don't, and I don't want to do that either, to tell the truth, and follow the textbook author's expression. So that completes section 3, except for 3.6. That probably will be left as an optional topic. I may or may not cover it as an optional video. As far as the regular topics are concerned, we just completed section 3.